moment. Okay, Tara Janelle, take it away.
All right, well, welcome everybody to this week's Schedule B seminar series for the Monsoon seminar series. Today we are joined by Christian France-Lanord from the CNRS in Nancy. And so today he's going to tell us a little bit about some of the work that he's been doing over the last few years involved with IODP. And pretty much without further ado, Christian, you can start sharing your slides.
Thank you, Tara. Yeah. So let's start. Thank you, Tara. And first, apologize for missing the talk last week. I hope this will replace it usefully. And I also want to thank Sarah, Peter, and Liviu for putting together all those conferences. This is a really good outcome of the wild use of Zoom in the scientific life. So today I will present some of the results we have on the view we may have on how the monsoon controls the weathering and the erosion style in Himalaya. And I will illustrate that both on examples on the modern Himalayan river system, erosion system, and on the past records from the Bengal fan. This work would not be possible without a lot of collaborations, and on top of that, certainly Martin Lupker, Beggatti's brother, Volker Spies from Bremen, and many others who have participated to this research very actively. So, as we have seen this figure many times now over those seminars, the monsoon is part of the development of the Himalayan orogeny, and very certainly the Indian monsoon is strongly driven by the presence of the orographic barrier of the Himalaya that allows very strong summer rivers, atmospheric circulation and precipitation over the Indian subcontinent, and certainly at the footwall of the Himalaya and the south flank of the Himalaya.
Excuse me, Christian.
Yes.
I think that your slide hasn't changed yet. You're still on the title slide.
No. Okay. Sorry for that.
That's okay. I was waiting to see if there was going to be a delay.
Yeah, it's not. I have a share is paused apparently. And I don't know how to. Does it changes?
I have it so that multiple participants can share simultaneously, and you should be able to share. I think you just unshared your screen.
Yeah, I did. I will restart.
Okay.
Once again, it's paused.
Okay, so that's your title slide.
And that's the next one, but you cannot see it, I guess.
No, it hasn't switched yet.
I have this strange orange bar saying that the sharing is paused.
Paused, interesting.
I never had that.
Yeah, neither have I. Let's see. Peter, are you there?
Yes, I am.
Have you had this issue?
Never.
because we are co-hosts, Christian and I, can you check as a host, the
Yeah,
primary host, if there are any settings that you need to change?
yeah. I don't see. There's a strange little green box showing an up arrow. I don't know what that means. Maybe I'll make him. I'll unco-host him and put him back on again and see if that helps.
So I stopped my sharing.
Oh, maybe that was just the sharing. So the green box disappeared. Let me try removing Christian as co-host and putting him back on. I don't understand how you can share one screen and just not go on to the next one, though. Ah.
Because we can see your slide layout here, where worst case scenario, we're not in full screen, but okay, so let's try that again.
Yeah.
It's still paused.
Try don't use the full screen, I think.
As soon as I am in, okay, yeah.
Yeah, we can see that.
Because we can see now the Indian monsoon, the Himalayan forcing slide.
Yeah.
So maybe instead of full screen, we can just do the presentation
Use
like this.
Yeah, yeah.
Ooh, that looks good.
That's good.
Okay.
Thank you for your patience, Christian.
No, it's
okay, I think we're all set to go.
I'll try to make it more simple. Okay. Okay, that's the best I can do, I think, to simplify the window. Okay, so let's start again by sharing the collaborators of this study, which have been numerous over the years, especially Volker Spies from Bremen for the oceanographic part, together with Herman Kudras, and in Himalaya, many PhD students have been working with Martin Lübker, Galley's brothers, Guillaume Morin, Sébastien Lénard, and so on. As I said, we have seen this picture several times now of the monsoon circulation of especially of the Indian monsoon, that is strongly controlled by the presence of the Himalayan orographic barrier, allowing reverse circulation, atmospheric circulation during the summer, and heavy precipitation over the Indian subcontinent and the south flank of the Himalaya for the summer. So the monsoon, as I will discuss it today, is essentially a system generating strong precipitation and seasonal precipitation. One of the important aspects of the monsoon is that it's part of the climate and tectonic interaction, or so-called climate tectonic interactions, whereby tectonics is the convergence between Asia and India that generates the Himalayan barrier that follows the development of the Indian monsoon. And which is in part responsible for a very strong erosion. The erosion generates tectonic or isostatic rebound of the range that allows to concentrate the uplift on a narrow band, and makes the Himalaya a very high range and narrow range, very homogeneous over 3,000 kilometers. This system more or less interacts and maintains the elevation of the range and the intensity of the monsoon. In parallel, this generates a very high flux of sediments that are transported by the river system throughout the floodplain and deposited in the Indian Oceans and Bay of Bengal and Indus-Fan, where we can study those records. Sorry, because I can't change the slide like this. Okay, so in this talk, I will essentially describe the monsoon as a climatic system that is the key driving force for the Himalayan erosion. It sustains the glacier supply. It allows landslide activity, maintains a narrow range and extreme elevation of the range. It is the driver of efficient sediment export from the mountains to the Bangladesh Delta. And it also allows a low chemical to physical ratio of erosion of about 2%. So we'll look at this on the modern system by comparing the Ganga and the Brahmaputra rivers, and so looking at smaller and more inner catchments like the Kudikola in central Nepal, or the Narani river, which drains the whole segment of the central Nepal Himalaya. So we look at a very high mountainous river catchment, a large Himalayan front river draining a good segment of the Himalaya, and the two main suppliers of sediments to the Bay of Bengal, Ganga and Brahmaputra. So this is a view of our cross section of the Kudikola segment. It's a non-glacier feeded river from draining the Himalaya from 5,000 to about 1,000 meter in elevations. It is covered with forest, but with two very active landslides, which are actually providing a lot of sediments to the river. You can see here the color of the river during the monsoon. And you can see here daily hydrograms of the monsoon, of the discharge of the river, showing that every night you have a peak discharge that generates a peak discharge of particles with sediment concentration that goes as high as 20 or 30 grams per liter of sediments transported by those. And although the landslides represents less than 2% of the area of the basin, it is actually responsible for 70 to 80% of the sediment discharge of the river. This is to illustrate how the monsoon works, and in this case, you have a time-lapse image of a landslide during the months of June, and you will see that with the monsoon progressing and the rainfall progressing, you have a big movements in the landslide that actually delivers sediments, breaks the rocks, and transfer sediments, pebbles, and blocks to the river. This figure here illustrates how the landslide actually progressed year after year since the 1960s to the actual extension in 2011. So that is the main process that generates sediments that goes into the river and that are further exported by those very large tributaries to the Ganga and Brahmaputra. There are altogether 13 tributaries that drains the Himalaya, very large segments of the Himalaya. Here, this is the Nahani River in central Nepal, Himalaya, 300 kilometer wide basins from east to west, draining several high peaks of the Himalaya, Dholagiri, Annapurna, and Manaslu. And this river is typical, shows typical hydrograms that is driven very directly by rainfall on the system. So you have during the monsoon on average a tenfold increase of the discharge and a very scattered discharge system, which actually generates peak or high variability of suspended sediments transfer. When looking at this in more detail, and this is a ADCP cross-section of the Narani at the footwall of the Himalaya, you can see that the velocity of the water can be very high as 6 meters per second in the core of the river, where it is able, of course, to drive a lot of sediments and pebbles at the bottom of the river. Altogether, a segment like this carries, from budgets we have been doing using daily measurements and depth profiling in the river, this river carries about 150 million tons of sediments per year to the floodplain. We now switch to the flatter Ganges floodplain. This is one of the flattest area on the Earth. The elevation at the outflow of the Narani is 120 meters, and we are still about 1,000 kilometers from the Bangladesh Delta. So the river slope is very, very flat, and in spite of that, there is a very high efficiency of transport of sediments from the mountain front to the Bangladesh Delta, and this is achieved because of the focused high flow, peak flow of the monsoon. This is the hydrogram of the Ganga in 2004 in Bangladesh. You can see it's rather smooth. There is a rather continuous peak flow that lasts for about 3 months of the monsoon from June to September. When looking at this kind of river, which is typically 3 to 4 kilometers large and with a very laminar flow, you have to take into account what happens in the water column, and we have adapted those techniques of sampling of sediments in the water column in order to take into account the sediment sorting that occurs in those rivers. So you have here typically what you find in the water column from the surface, fine sediments, fine silt, to the bottom bedload sand that is carried by those rivers. Of course, the grain size increases with depth, and the sediment concentration increases from typically 1 gram per liter at the surface to about 6 grams per liter near the interface with the bottom. These grain size changes can be appreciated with geochemical parameters such as aluminum to silicon ratio that we like to use. Aluminum to silicon ratio responds to the mixing between sand, quartz-rich sand, and clay-rich silt and fine silt, which are aluminum rich. And you can see that there is a good correlation between this aluminum to silicon ratio and the D84 here, which is high for sand, around 300 microns for the Ganga, and about 10 to 20 microns for the fine silt. So here you have, again, ADCP profiles of 2 very different regimes for the Ganga in Bangladesh, with about high peak flow of 40,000 cubic meter per second for the top sections, with very high velocity in Ganga with 4 meters, and a more quiet day. And you can see that the sediment concentration for the peak flow is very high, It's typically 10 times higher with 2 to 3 grams per liter in the water column. DAT4 or grain size is increasing very strongly. Aluminum to silicon ratio is much lower during the peak flow season. And definitely, this is thanks to the increase of the peak flow that sediments are transported and sand is transported from the mountain range to the Bangladesh Delta. These measurements and taking into account the hydrological regime allows to model relatively well the quality, the intensity of the sediment flow, and that has been done by Martin Lupker for the Ganga in Bangladesh, showing that the transport of sediments was estimated around 400 million tons per year. And that approach allows also to estimate the aluminum to silicon ratio of the suspended load or the sediment flux, which is here in this case close to the average of the continental crust with a value of 0.23. So this gives a first illustration of what happens from the mountain to the Bangladesh Delta. We look at here on this cross section of aluminum to silicon ratio. Average bedrock has a value around 0.22 at the outflow of the Himalaya, and estimated from the rivers such as the Narani. And there is a slight increase of the aluminum to silicon ratio from the Himalayan front to Bangladesh, which is due to sequestration of sand in the floodplain. And this sequestration is about 10% of the total flux of sediments. Sand is deposited in the floodplain. It is illustrated here with chemical composition of seawalls or cores in the floodplain. And similarly, again, in the delta, you have a sequestration of sediments, which has been very well illustrated by studies by Stephen Goodbread. And we have, again, relatively aluminum poor sediments deposited, sandy sediment deposited in the delta. That further tends to enrich the sediments from the estuary, but we have no very reliable measurements that allows to make a safe average here. So we don't really know what is exported to the shelf of the Himalaya. What we know is that there is a lot of sand that is transported there as well. So those sediments can be used to actually scale the erosion rates, and that's an approach we have been following quite seriously on those rivers. And using cosmogenic isotopes such as beryllium-10 on quartz that is produced in situ in quartz, you can estimate from the concentration of beryllium-10 the production of this beryllium and the erosion, and transform this into erosion rates. It returns for the Ganga relatively homogeneous data in Bangladesh with erosion rates that are in the order of 1 millimeter per year for the whole size of the basins. And that corresponds to a transfer of about 600 million tons per year, slightly higher than the actual measured flux of sediments transported by the Ganga. But this kind of measurements integrates, of course, production of beryllium-10 over thousands of years. For the Brahmaputra, we have a much more variable concentration between 25 and 46 atoms per gram. But here, this translates into erosion rates which are in the order of 1 millimeter per year as well, and a much higher flux of particles than the Ganga, typically 800 to 1400 million tons per year. So now we switch to weathering. Weathering is closely linked to monsoon rainfall and physical erosion. Monsoon, because the water is essential for weathering. It's the main chemical driver of the weathering. And physical erosion is a facilitating agent of weathering, as it generates or creates reactive surfaces. The byproducts of weathering are, of course, dissolved elements transported by the rivers that can be easily measured on modern rivers, and secondary minerals, clays, iron oxides that can be examined on those rivers as well. So this is an example of what we get when we compare Himalayan front rivers to rivers in Bangladesh. And I'm just comparing here one soluble element like potassium compared to aluminium, all normalized to silicon. What we can see is that we have a good correlation of those potassium to silicon ratio and aluminum to silicon ratio. And thanks to this fact that we look at mixing relationship, we can characterize relatively well the loss of potassium due to weathering from Himalayan front to the Bangladesh Delta. And this approach allows to actually calculate how much potassium is released by weathering in the floodplain. You have similar processes occurring for other elements like sodium here in that case, which is the main cation supplied by the silicate weathering in the Himalaya. Or here, secondary hydration that is measured, that illustrates the generation of clays. Chemical erosion can also be easily measured by looking at dissolved flux. This is well done on the Ganga and Brahmaputra rivers by several studies. And it's easy to measure the dissolved flux. It's a little less easy to share the part of silicate and carbonate weathering, but that can be achieved through several different approaches and budget views. And we can see here that the silicate weathering delivers essentially sodium and potassium with little magnesium and calcium. And this appears minor compared to carbonate weathering, which is the main provider of dissolved species in the river. This is altogether looks relatively small compared to the sediment flux, which is much higher. And in fact, that is a characteristics of the Himalayan erosion, that it is a system dominated by physical erosion. With here on this world compilation by Josh West, where you can see Himalayan rivers and Ganga Brahmaputra in this diagram, comparing total chemical and physical erosion to silicate cation denudation rates. And you can see that Himalayan rivers and Ganga Brahmaputra are characterized by much higher or low ratio of chemical to physical erosion. And this belongs to the families of rivers which are actually where the weathering is kinetically limited. In other words, the sediments are transported or exported too fast to be efficiently weathered. Another very interesting part of the sediments with respect to weathering is carbonates. Carbonates are very easily dissolved by as long as you have water in the system. And one of the particularities of the Himalayan system is that it transports a lot of carbonates, especially on the Ganga. The Ganga exports about 6% of carbonates, whereas the Brahmaputra, which has much more water, exports only 0.4 wet percent of carbonates. This is partly linked to the geology, and here we can see the difference between the Narani River and the Kosi River. Narani River has high peaks in the Tethys Himalaya, carbonate-rich formation, geological formations like Dholagiri Peak and Annapurna peaks, which makes that there is a lot of carbonates in the sediment load. Whereas the Kosi, which joins the Everest, has Tethys Himalaya restricted to the northern part of the basin and less exposed to erosion. So as a result, here we have a geological control on the export of carbonates to the rivers. But altogether, those rivers, for most of them, have a high carbonate flux. And in fact, what actually controls most of the export of carbonates is the runoff. And there is a relatively good relationship between the runoff and the chemical erosion of carbonates, which shows that as long as you have water, you have a higher chemical erosion of carbonates. So this is a summary and comparison of the Ganga and Brahmaputra rivers. Ganga is in red, Brahmaputra in blue. We have here the runoff of those rivers. The runoff of the Ganga is much lower than that of the Brahmaputra. This is a permanent feature of the Himalayan monsoon or the Indian monsoon, which makes that the western Himalaya is drier, and especially the western part of the Ganges, the part drained by the of the western part of the fruit plain is much drier than the eastern Himalaya. And this, as a result, generates higher silicates weathering, chemical denudation for the Brahmaputra, for both silicates and carbonates. The numbers here are in 10 to the minus 2 millimeter per year. That is compared to the physical erosion in millimeters per year, which is much, much higher indeed. But once again, the silicate weathering is the silicate physical erosion is really higher for the Brahmaputra than for the Ganga. So altogether, we have a system where the monsoon is more intense on the eastern Himalaya for the Brahmaputra, which generate higher chemical erosion, chemical denudation of silicates and carbonates, but also of physical erosion. As a result, the ratio of, and this can seem paradoxical, but the ratio of silicate to chemical erosion is higher on the Ganga than on the Brahmaputra, just because, in fact, the amplification of the physical erosion is stronger. So even though the Brahmaputra is a river with higher chemical denudation than the Ganga, when you look at the sediment load of those sediments, you would say that chemical erosion is more intense on the Ganga than on the Brahmaputra. So there is ambiguity when you look at the sediment results. You may say that, okay, I have a system with more intense chemical weathering in the Ganga than on the Brahmaputra, but in turn it turns out to be wrong if you look at the net chemical erosion denudation. When we examine those situations, the Ganga and the Brahmaputra have differences others than monsoon precipitation, and this is essentially linked to the geometry of the fruit plain. The Ganga has a large fruit plain which allows a long residence time of the sediments, whereas the Brahmaputra is much more channelized, tectonically restricted, which channelize the sediment transport. This should restrict the weathering, the rapid the short residence time, and whereas in the Ganga, the long residence time should also slow or reduce or increase the weathering. But in fact, it's the dry condition and in the Ganga and the wet conditions in the Brahmaputra that makes the contrast in weathering intensity high in the case of the Brahmaputra and lower in the case of Ganga. And this is clearly linked to the chemical or the climatic contrast between the two rivers. So we'll now follow the erosion, or what we can say of the erosion in the past, by looking at the records of the Bengal fan. So everybody's familiar with the Bengal fan. It is the largest fan draining the largest fan of the world. It's draining all the central and eastern Himalayas through the Ganga and Brahmaputra rivers, and it extends for over 3,000 kilometers south of Bangladesh. And the average thickness is about 4 kilometers, but it can be much deeper in the just south of Bangladesh. We will look at three types of sediment record. Here, for the very young sediments, we will look at the shelf and swatch of no-ground canyon, submarine canyon of the submarine delta of the Ganga Brahmaputra. We will examine some channel levee system at 16 degrees north that were drilled by Zone Cruise and Herman Kudras and Volkach Peace expeditions. And finally, the long-term records as retrieved by IODP Expedition 354 at 8 degrees north in the middle fan. So sediments are exported by the Ganga and Brahmaputra rivers to the delta. They arrive on the shelf, and they generate turbidity currents, which are transported downslope throughout the channels. Those channels builds progressively levees that accumulates on the fan, and those channels also transport massive quantities of sand, which can expand as sand lobes in the system. When looking at large-scale seismic structures, such as the work by Tillman Schwenk and Volkach Peace at three different latitudes here on the Bengal fan, we can see that the fan is built by the accumulation or the superposition of channel levees intercalated by sand-rich sediments all throughout the depths, and this is true at different latitudes of the fan. So this clearly illustrates that depot centers is variable and can migrate from east to west. And because of that, the strategy we developed during Expedition 354 on the Bengal fan was one of drilling of a transect, an east-west transect at 8 degrees north, in order to retrieve a sedimentary record as continuous as possible. So this is the 7 sites which have been drilled between the 85 East Ridge and the 90 East Ridge at 8 degrees north in the Bay of Bengal. This is all in international waters. And 3 deep holes at about 1 kilometer long record the Neogene time scale from lower Miocene to present for U1451. And the 7 more shallow sites documents well the Pleistocene deposition. So turbidites here are characterized by high accumulation rates and deposition of alternation of centimeter to 10 centimeter thick turbidite pearls from fine silt to sandy sediments. And this is intercalated when it is not levees by very sand-rich deposition with no apparent structures and very sandy characteristics of those sediments. When we look at the aluminum to silicon ratio of those sediments in blue for the Bengal fan and compared to the lower Meghna sediment, river sediments we have, we can see that the dispersion of aluminum to silicon ratio of Bengal fan sediments is exactly matching with what we observe in the modern rivers with very sand-rich sediments in sand lobes, and silt, very fine silt for some of the levee deposition. When there is no deposition of turbidites, because turbidites are more or less deposited in those channel levee systems, there is deposition of slowly accumulating hemipelagic deposition. This is calcareous clay-rich ooze with a lot of biogenic material, 30 to 60%. They are very different. They are characterized by bioturbations, and we will not look at these today, as they represent their detrital characteristics are quite different from those of the typical Himalayan river sediments. They are more mixed with other sources. The deposition has been quite discontinuous on this record, and especially during the Pleistocene. And this is the work by Bergman, which showed how the fan deposition actually migrates relatively rapidly. And we have here the position during the middle Pleistocene between 1.2 and 0.7 million year. We have fan deposit. We have lack of deposition all throughout our transect, and so transfer is restricted to the western part of the fan. Then it returns to the central fan here during the 0.7 to 0.25 million year. Before to migrate again to the west in the present period. So there are very wide, large variability of depot center and fluctuations. This is quite similar, of course, at the long term, but less detectable. Although here between the three sites we have changes in accumulation rates, but the central record of the fan shows steep accumulation rates, very high accumulation rates, which are continuous throughout from Miocene to present, with no strong variability in the accumulation rates. I go very fast on the origin of sediments. This is work by Albert Gani using strontium and neodymium, demonstrating that the characteristics, the growth characteristics of those sediments have not changed very strongly throughout since the Miocene, and corresponds well to the mix between the what we document on the modern system between Brahmaputra and Ganga, so Himalayan and Trans-Himalayan mixing in the system. More relevant to the erosion regime also is the presence of sand in the system. What we can see is that the top section has a lot of sand. This is the yellow color here, whereas the bottom section documents or records less sand. This is linked to the drilling techniques, and with rotary techniques we cannot recover sand very efficiently. But when we document actually the presence of sand using indirect tracers like penetration rates, we can see that even at depths there are very high penetration rates in the order of a meter per minute. Here, even at 1,000 meters below seafloor, which indicates the presence of loose sand in the record. And when we look at the restitution of this penetration rates in terms of sand, coarse silt, and fine silt, we can see that the sand proportion exported to the system is very high, remains very high. So this is what we get on the aluminum to silicon ratio budget or image when we continue the journey to the fan. We have deposition of very fine silt in the shelf on the shelf edge and on channel levees. But when we look at the middle fan at 8 degrees north, there is a lot of probably like 40 to 60% deposited as sand with coarse composition, low aluminum to silicon ratio, as documented in the bed loads or in the fluid plane, and we have levees which are enriched in aluminum to silicon ratio. But the system has the ability to export sands very deep in the sea. So this is now we switch to erosion rates. This is again the beryllium-10 cosmogenic beryllium-10 work by Sébastien-Lénard, documenting paleo concentration of beryllium-10 as far as 6 million years. This is the first time we can actually do this kind of measurements on marine sediments and marine cores, because it's demanding a lot of material, typically a kilogram of quartz for very old sediments. And what we document here, especially for the Pleistocene, is that we have a system where the paleo concentrations of beryllium-10 are rather homogeneous throughout time. There is no huge variability. And this translates, compares very well with what we measure in the modern Ganga and Brahmaputra or lower Meghna rivers, documenting erosion rates in the range of 1 to 0.7 millimeter per year, very comparable to the modern measurements we have with this system. So altogether, a system where erosion rates remains relatively steady in spite of the very strong changes in climate variability and the installation of the Pleistocene glacial interglacial variability. Weathering now is the last part I want to document here. So I'll go relatively fast. This is again potassium to silicon ratio compared to aluminum to silicon ratio. It is quite homogeneous, whatever the age is for the Bengal fan. And when we compare it to modern rivers, Himalayan front in green and lower Meghna in yellow, we can see that the Bengal fan from all time is kind of intermediate between the Himalayan front rivers, the today's Himalayan front rivers, and the lower Meghna, the estuary of the Ganga Brahmaputra. In other words, the Bengal fan record for potassium appears to be less weathered than the modern river, the modern lower Meghna. We can have a look on carbonates. Carbonates are quite interesting and quite sensible to monsoon and runoff. As I mentioned already, in the Bengal fan, the situation is a bit more complex than in river sediments, as we have more mixed sources of carbonates. And here, this is a view of the delta C13, delta O18 isotopic composition of carbonates in the system. We have obviously a mixing between two sources. One is the detrital carbonates, which is inherited from carbonates from the rivers, which are dominantly from the Tethys Himalayan formations. Those carbonates are marine limestones metamorphosed and which are depleted in O18 by metamorphic reactions. And in the Bengal fan, it is of course mixed with some marine biogenic carbonates, which are contemporaneous of the deposition of the turbidites, which generates this mixing relationship. But we also have a third end member which is very likely diagenetic, produced by reactions such as sulfato reduction in the sediment column. So we have a significant proportion of diagenetic carbonates in these systems. But thanks to the isotopic footprints, we can decipher this mixing and restitute detrital carbonate proportion. What we can see is that in the past, and especially during Miocene, the proportion of detrital carbonate was pretty high as 7 to 8 weight% in this late Miocene period. Then it decreased significantly to reach typical value of the Pleistocene around 3 weight%, which is significantly higher than what we find in the lower Meghna on average. In the Miocene, there can be a geological control on that. The Tethys Himalaya can be more exposed to erosion during the Miocene period, and that a likely explanation for the high presence of carbonates in the late Miocene is possibly the high exposure to the erosion of the carbonate formations. But for the more recent deposition for the Pleistocene, the modern configuration of the Himalaya has not been changing very significantly. And there is an indication that there is less carbonate dissolution in the during all the Pleistocene than during the more recent Holocene period. So we can now compare this with a more shorter time record from the levee at 16 degrees north, and this is the work by Morten Lupker and Chris Hein on the levee at 16 degrees north, looking at potassium to silicon ratio here and detrital carbonate abundance. And what we can see is that both signal indicating more weathering on the left increases or weathering increases with the climate optimum and the Holocene deposition compared to the last glacial maximum configuration, where more carbonates were present in the section and more and less weathering of the potassium. And this goes together with monsoon intensity. This is documented here by the delta D of fatty acids, as Gali has been showing a few weeks ago. And so when the monsoon was strong, when the monsoon was weak, we had less dissolution of carbonates and less weathering of silicates. And when the monsoon intensifies, we dissolve more carbonates and have higher weathering. This seems to be relatively logical, and so dry climate that occurs during the last glacial maximums favors low weathering and low dissolution of carbonates. In addition, we have a sea level low stands, which allows faster transport. The rivers are more channelized in the floodplain due to incision. In spite of that, during the interglacial, the wetter climates and slower transport due to a flat floodplain could explain higher or increase of weathering. That is a possible explanation indeed, but what is quite makes more complexity is that for both potassium to silicon ratio and detrital carbonates, we observe that the modern situation, the today's situation documented by the rivers, as I've been showing in the first part of the talk, show much more extreme situation with higher chemical weathering, loss of potassium, and more stronger dissolution of carbonates in the sediments. And of course, one has to consider the possible anthropic forcing in this system. Anthropic activity is intense in the floodplain. More than 600 million people are living in the delta and floodplain of the Ganga and Brahmaputra. There is total deforestation, overgrazing, intense clay mining, sand mining, acid rain, and on top of that, embankment of the rivers, especially for the tributaries of the Ganga and for the upper Brahmaputra in Bangladesh. But the embankment should reduce the weathering and doesn't seem to play strong. But soil erosion and acidification seems to be factors which could increase the weathering. So I'll finish with this, just to mention that at the Pleistocene timescales, we have relatively steady erosion rates with no strong detectable response to the glacial interglacial variability, and that suggests mostly a tectonic control on the intensity of the erosion rate, with a weathering which would be more sensible to monsoon intensity. At the Neogene timescales, we have high deposition rates at 8 degrees north, high sand export at 8 degrees north, overall low weathering intensity of the sediments that is persistent all throughout the system, and high and steady erosion rates, at least for the 6 to 0 million year period. So this is coherent with the presence of a high range exposed to monsoonal climate since at least 20 million years. So with this, I will finish my talk and take questions. Hopefully I'm not too late, a little late. Sorry for that. Thank you very much.
Great, thank you very much, Christian. So for all of us here in the seminar, please remember to type your question into the chat, and then we can either read it out for you or we can call on you and then you can read it out for the speaker. So give you all a moment here to compile your questions. Everyone is still percolating all of their thoughts now. Okay, here we go. Several. Excellent. So the first question we have is by Rasmus Teed. And so you have a comment and one question. So would you like to?
Yeah, thank you, Christian, for the lovely talk. I have, for the first, you showed the carbonates dissolution, what you referred to the Tethyan sediment section decreases from the late Miocene Pleistocene time. This is, I think it's very well explained with the establishment of the high Himalayan front evolving prominent orographic barrier from at least 10 to 12 million years, and it explains very well what the decrease of accessibility to dissolve the carbonates in the Tethyan section. So I think your results show very nice, and that's one of the very nice ways you show that tectonic processes might influence your signals in the Bay of Bengal. However, I have kind of what I'm very surprised is that you can't see the Shillong Plateau uplifting kind of 14 to 10 million years and enormously recycling all the cover sediments of the Shillong Plateau. So I'm astonished that you don't recognize this at all in the Bay of Bengal fan signal.
Yeah. For me, well, it's not, there is clearly that is more detectable using the records of strontium and neodymium that I have not commented in detail, and that would require more talk by Albert than I. But so the Shillong Plateau will tend to generate sediments which have isotopic characteristics comparable to, say, the Lesser Himalaya, to be on the average, although there are also other lithologies which are important there. What I'm not sure, well, we see an increase of the Lesser Himalaya erosion that takes place in the late Miocene in the system and during the Pliocene. That is very clear from the strontium and neodymium record, but it is also coherent with the development or the tectonic development in the Himalaya, with the uplift of the MFT and so on. So it is difficult to decipher what is coming from, what is linked to Shillong and what is linked to the Lesser Himalaya. What I'm not sure of is how much sediments could be derived from the Shillong Plateau. How much? What does it represent in terms of mass of sediments, and whether it is detectable in a way.
Okay, thank you very much.
Okay, let's see. Our next question is by Peter Clift. So Peter, if you could ask your question. I see you've got a couple listed here.
Yes, that's right. So Christian, you were showing that the sediment deposited sort of in the Holocene as the monsoon got stronger was more, is it more weathered? And I wondered if you thought that was a direct effect of the monsoon climate, or whether that just reflects, yes, that one. Yeah, does this reflect just more reworking of the floodplains, or do you think this is chemical weathering that's actually happening sort of synchronously with the, you know, rather than...
There are several aspects there. Well, you can consider it straightforward and say this is perfect. There is a dry climate and you have low weathering and low dissolution of carbonates, and you have wetter climate and everything goes simple. Okay, that's the simple explanation. That seems easy. On the other hand, there is the geostatic fluctuation, which makes that the base level of the rivers are actually changing. And during the last glacial maximum, the river is more incised. The Ganga and the Brahmaputra have valleys in Bangladesh, and what is the consequence of that is not so clear. What is clear is that there is no significant input of erosion of the floodplain and delta deposition, because this would return weathered sediments with no carbonates. But we are at the end of the glacial period here. We do not document the full glacial period, so this would take a more complete record of an older record of the first 30 or 40,000 year old that we don't record or present here. So this is where we are standing. And of course, there is also the fact that the modern river sediments appears much more extreme, and that there might be an influence of the anthropic forcing. Would it be able to start 5,000 years ago is a question mark.
Yeah.
We have seen a presentation 2 weeks ago, I think, for the Indus, suggesting that there could be an increase of weathering due to anthropic forcing on the western side. There is no such indication on the eastern side. I would tend to consider that the anthropic forcing should be effective more in the historical period than in the prehistorical. But who knows? I mean, these are open questions for now for me.
Thank you. Thank you. And I was a bit curious about the cosmogenics, actually, because I guess there isn't a seismic budget for the Bengal fan yet, but
not yet, yeah.
Right. Well, in some ways, it's not a very good question then. So in most places, of course, it looks like the seismic budget suggests faster erosion in the last few million, which often seems to be at odds with the cosmogenic isotope budget. I just wondered if you had any thoughts about why the seismic or the seismically derived sediment erosion rate rather than the cosmogenic erosion rate would be different.
Well, the seismic budgets which have been done for the Bengal fan are essentially wrong, and we knew that from long, because they were based essentially on margin records and extrapolations of deposition on the margins. Here, when we consider both the deposition at 8 degrees north for U1455 and U1450, there doesn't seem to be a clear change of deposition due to the Pleistocene. It's a bit different from U1451, which shows a relatively low accumulation rates during the Pleistocene, the Pliocene and upper Pleistocene. But this is linked to tectonic deformation on the 19 East Ridge, which makes that no turbiditic deposition occurs there. And we have a very long hemipelagic deposition marked here in blue. That explains this relatively low accumulation rates during the Pliocene period. So as far as we can tell from the U1450 and 55, which are more independent of tectonic deformation in the Bengal fan, there is no strong contrast of deposition between Pliocene and Pleistocene.
Thank you.
Okay, and I think we've got time now for about one last question, and we have a question here by Ximing. So would you like to ask your question? Or...
Yes. Hi, Christian. Yeah, good to see you. Yeah, in fact, my question is similar to Peter's, and it's very interesting to see the barium isotope record. And it's surprising that the erosion rate in the Bengal fan was very, very stable since the last 7 million years. I'm just curious, you know that the monsoon intensity or the tectonic activity or the temperature should change largely since the late Miocene. Why the erosion rate just keep stable?
Well, that's a difficult question to answer. This is what we observe, and therefore the implication is that the climate change does little, or at least the climate variability, which is the basis of the Zeng and Molnar hypothesis, that the climate variability, the glacial interglacial alternation, could enhance the physical erosion worldwide. This doesn't seem to operate in the Himalaya. And that is possibly because the dominant control on the erosion rates in the Himalaya is essentially the tectonic, and the tectonic is not changing at that time scale. The convergence between India and Asia remains the same, and the shape of the Himalaya probably remained quite similar. And the variability in glacier cover at that time scales is probably not efficient enough to drive significant variability. In the detail, you have to keep in mind that glacial or cosmogenic isotopes integrates a relatively large period of erosion. So it's not clear whether we can really decipher variability at the glacial interglacial time scale, although the transfer time in the fluid plain are considered to be relatively short, in the orders of a few thousand years. So if there was a big change in the erosion rates, between a glacial period and an interglacial, we should see it. But once again, that's maybe something we have to consider critically.
Thank you, Christian.
Great, thank you. So I believe that all the questions that we should probably have for today, and I think that's all of them within the chat. So again, everybody kind of put your hands together to give another applause to our speaker for today, Christian. This was an excellent talk and an absolute monumental amount of work by you and your team. It's been a pleasure to see that today. So before all of you run away, I just want to make sure that you stay tuned for the next talks in the seminar series. And so actually we have one later today by Peter Clift at around 5 p.m. London time. So remember to stay tuned if that is in your time zone of interest. And then next week on the 23rd of June, we will be having Mara Lamonta give her own seminar here as part of the Schedule B series. So again, I hope everybody has enjoyed the talk. Stay tuned, and I guess everyone should have a nice rest of your day. Yeah.
Thank you very much, Tara.
Okay, thank you again.
Thank you.
Bye, everyone.
Bye.
Bye.
Ciao, ciao. Ciao, ciao.